congruent and similar triangles today. When you're looking at congruent triangles, you need to have every single part of each triangle congruent to the other part. So for example, in this picture we have triangle ABC congruent to triangle DEF. We call this as the symbol for congruent. So angle A is going to be congruent to angle D. Angle B is going to be congruent to angle E, and angle C is going to be congruent to angle F. The order that you write the congruency statement really matters because it's going to tell you which angles are congruent. It's also going to tell you which sides are congruent. So for example, side AB is going to be congruent to side DE. So AB is going to be congruent to side DE, and we can see that in the diagram by the markings. Okay. Corresponding sides and angles must all be congruent. So that's what we just talked about here. Look for it in the diagram or the congruency statement. All these sides are going to be congruent. All these angles are going to be congruent if the two figures are congruent. Now, there's 4 different ways that you can prove for a fact that triangles are congruent. And this is the type of question that I've seen most often on the released items on the AIM. So you want to familiarize yourself with these theorems and be able to figure out which one you have. So the first one is what we call SSS, or side, side, side. And that's when you know that all 3 sides of one triangle are congruent to all 3 sides of the second triangle. You might not know anything about the angles, but if you know all 3 sides are the same, you know that the triangles are congruent. The second one is SAS, or side angle side, and that's when you have 2 sides and the included angle that's congruent. So what I mean by included angle, I mean the angle that the 2 sides that are congruent form. So if you look at this triangle down here, we know this side is congruent to that side. We know this side is congruent to this side, and the angle that those 2 sides make is congruent in the first triangle and the second triangle. So that's side, angle, side. The third one is going to be angle, side, angle. So that's where you have 2 angles and the side that's included between the 2 angles. So here we have this angle and this angle congruent in the 2 triangles. And then the side that connects those 2 triangles is congruent in each of them. And then the last way is angle, angle, side. And again, that's 2 angles and the non-included side. So here we have this angle congruent to that angle, this angle congruent to that angle, and then one of the sides that is not the side in between the 2 angles is the one congruent. Just like here, the S is not in between the 2 A's, the way we write it. The congruent side is not in between the 2 angles. Alright, now let's talk about similarity. Similar triangles are all about proportions, setting up proportions and solving for your missing variable. When you have 2 triangles that are similar, the angles are going to be exactly the same. You have to have some way of knowing that the angles are exactly the same. Then the sides are going to be proportional. So let's look at this example here. We know that triangle HIJ is similar to triangle GKL. And by the way, this little squiggly is the symbol that we use for similar. So in this particular picture, side IJ is to side KL as side HI would be to side KG. So we can complete that ratio like that. This is a proportion. This side is to this side, that side is to that side. Then we know if we have GL down here, that's going to match up with side HJ up here. So any one of these pairs of sides can be set up to set up a proportion that you need to solve for a missing variable. So let's take a look at an example how you would set this up and solve for x. Here we have 2 similar triangles. We know triangle ABC is similar to triangle DEF. Now pay attention to the similarity statement because it's going to tell you which sides correspond when your triangles are labeled. You know that, for example, side AB is going to match up with side DE. And that can really help if your triangles aren't drawn in a way that it's easy to tell how they match up. So for example, I know that 8 is to 16. Look for where your variable is. It's over here. There's my x. As 12 is to x. So then if I want to solve for x, I'm going to cross multiply. 8x is equal to 12 times 16 which is 192. Better check my math on that one. Divide both sides by 8, and we get 32. X is equal to 24. Okay? So look for your matching sides, solve for X by cross multiplying. Now let's talk about different ways we can prove triangles are similar. And I've seen problems like this on the released Ames items as well, where you have to identify what information you have and whether or not that's enough to show for a fact that two triangles are similar to each other. So there's only 3 ways we can do this. The first one is SSS. Now when you're proving similarity, this doesn't mean that all 3 sides are congruent. It means that all 3 sides are proportional. So if you look at the 3 sides that you have, let's look at my triangle, which appears to be, I always like to go smallest to biggest because it's easiest to set up for me. So in this first triangle, it appears that C is the smallest side. Over here, F is the smallest side. So C over F must equal medium to medium, so A over D, and that must equal large to large, or B over E. So all 3 of these sides have to be proportional. All 3 of these ratios have to be equal. The other way is side angle side. So this is where you have 2 proportional sides and 1 congruent angle, and the angle that's congruent has to be in between those 2 sides. So A over D must equal B over E, and these 2 angles have to be congruent. Now the last way that you can prove similarity is what we call angle-angle similarity, and that's where you know that 2 angles of one triangle are congruent to 2 angles of the other triangle. Because if you know that 2 are congruent, you know actually that that last one is going to be congruent as well, because all the angles have to add up to 180 degrees. Alright, here's another example. Can we tell for a fact whether or not these triangles here are similar? And this is one of those situations where they're not in the same orientation. One's been kind of rotated and flipped. So the way that I like to do this, like I said, is small over small, medium over medium, big over big. So I have all 3 sides of the first triangle, all 3 sides of the second triangle. The smallest side of this one is 6, the smallest side of this one is 8. 8 over 6 reduces to 4/3. In the medium side of this triangle is 9. The medium side of this triangle is 12, so 12 over 9, the bigger triangle over the little one, reduces to 4/3. And then we have the longest side, so big over big. Here the biggest side is 16, here the biggest side is 12, and again 16 over 12 reduces to 4/3. Since all 3 of these ratios are the same, we can say that all of the sides are proportional. The triangles would be similar by side, side, side similarity. Alright, now for our last part, we're going to talk a little bit about scale. Scale is really all about similarity, although you might not have similar triangles or similar polygons, but the idea is the same. So a scale shows the relationship between similar models or drawings. So some examples are like blueprints. A lot of times we draw blueprints because we're giving a scale drawing of what a building or a layout of a building might be. You guys might have seen scale, like little model cars, which are exact replicas of big cars, and that's what we're going to talk about in the example here. So that's the idea of scale. Oh, another example is like when you Xerox something and you shrink it down, that's another example of scale. So we're going to use the scale that's given to set up a proportion to solve the problem. So in this example, George made a scale model of a car using a scale of 1 to 7. If the length of his model car was 1.54 feet, what is the length of the original car? Now we know that the model car is the smaller car, so that's matching up with the 1 in our ratio of 1 to 7. So think about our ratio. The model car to the original car is going to be in the ratio of 1 to 7, and that's going to equal the length that we know for the model car, 1.54, to the length that we're looking for, which is x. You could call it any variable you want. So now we cross multiply, so 1 times x, or 1 times x, is equal to 7 times 1.54. And 1x, of course, is just x, and then if I multiply 7 times 1.54, I get about 10.78 feet. So just use the scale that you have, and think about the part that you know and the part that you want to know, and where those parts go in your ratio. Okay, we're all done for today. We'll practice this on Monday.